My dear students, on today's video we are going to see a 4-bit parallel adder. First we'll see what happens in full adder. Full adder is a circuit which performs addition of two single bit numbers with carry. So assume A is the number with bit A0 and B is the number with B0 bit and C in is the carry. So in this full adder they are going to perform addition of A0 and B0 with the C in and produces output sum and C out. This is a full adder. And now the today's topic is 4-bit parallel adder. If you want to perform a 4-bit parallel adder, then we need 4 full adders, because a single full adder performs addition of 2 bits of 2 numbers, and here we want to perform addition of 4 bits of 2 numbers. So number A with the A4, A3, A2, A1, and number B with the B4, B3, B2, B1. Hence, for the implementation of 4-bit parallel adder, we need 4 full adders. In the same way, if you want to perform addition of n bits, then we need n full adders. How it is? Let's go through. Suppose number A having an to A0 bit and number B having bn to B0 bit. So to adding each and every bit we need 1 full adder. In this way, if we want to perform addition of n bit numbers, then we need n full adders. And let's start with the today's topic, that is 4-bit parallel adder. For the 4-bit parallel adder, we need 4 full adders. This is the first full adder, that is MSB. This is second full adder, second MSB bit. This is third full adder, and this one last LSB full adders. 1, 2, 3, 4 with the inputs are A0, B0, A1, B1, A2 and B2, and last one is A3, B3. So these are the one input, and first input to LSB is C in, produces output sum and C out. This C out becomes input for the next. So output of second is sum and C out. C out is the input for the next full adder, and outputs are sum and C out. Again this C out is the input for the next one, and outputs are sum and C out. This is the block diagram of simple 4-bit parallel adder. Okay, let's see in which way the carry or whatever the result is propagated from one adder to another adder. Assume the bits are, first full adder is A0, B0, C in, and outputs are sum and C out. First assume this will be 1, this will be 1, and carry will be 0. Then sum will be 0 and carry will be 1. So this is the output of first full adder. So this will be comes carried for the next in C in. So here C in, here A1 bit, here B1 bit. Outputs are sum and C out. These are the outputs of second full adder. Assume bits are 0 plus this is 1. So carry will be 1, C out will be 0. This is output of second full adder 2. So again for the next full adder, just this carry is propagated to next C in. So this will be acts as a C in. Outputs are sum and same C out with the bits of A2 B2. Let's value of A2 is 1 and B2 is 1 plus C out is C in is 0. So 1 plus 1, sum is 0 and carry will be 1. This is the output of third full adder. In this way we can again go through last step. This is the input as a C in. Here A3 B3 and C in produces output sum and C out. So assume the value of A3 is 1 and B3 is 0 and C out is a 1. So sum is 0 and carry will be 1. In this way, if you observe carefully, whatever the output of first, that is sum and C out, or C out is the carry out, it will be C in for the next. The C out of the second full adder is C in to the next, and this is called as ripple carry adder, because the carry is propagated from the one full adder to the next and next to the next one. So it is called as also ripple carry adders. Let's see with one more another point of the 4-bit arithmetic operation is 4-bit subtractor. To start a 4-bit subtractor, let's find out in which way in the digital circuit subtraction is carried out. In digital circuit, especially for the digital computers, the subtraction is carried out by using 2's complement. By using 2's complement. What happens? Suppose we want to subtract number B from A. Then we have to take first, we have to take 2's complement of number which is going to subtract. So number B is going to be subtract. So we have to take a 2's complement of number B. How 2's complement is calculated? First, assume number B will be 0 1 0 1. This is a number B. Okay, and number A assume is 1 1 0 1. This is the number A. So for the number B, first take 2's complement, and 2's complement is calculated by first by getting 1's complement. How 1's complement are calculated? Defined. The 1 complement is calculated by inverting all the bits of number B. So number B are 0 1 0 1, and after 1's complement it will be 1 0 1 0. Once you are able to find out 1's complement, then second step, add value 1 in LSB bit. So this is LSB bit, and according to this rule 1 0 1 0, we have to add 1 into LSB bit, and the value becomes 1 1 0 1. In this way we can perform a 2's complement, and after getting the 2's complement result, this number is added with the number A, like 1 1 0 1 is added with the 1 0 1 1. So 1 plus 1 0, carry again 1 1 plus 1 0, carry again 1 1 plus 1 0, carry again 1 1 plus 1 0, 0 plus 1 1, and value carry is 1. So this is the number, or that is total result. If you go through, I will just clarify here. 8 plus 4 12 plus 1 13, 13 into decimal 1 minus 4 plus 1 5, it will be 0 8. So this will be equivalent 1. So first we have to take a 2's complement of number which is going to be subtract. The 2's complement is calculated by first 1's complement. 1's complement is nothing but inverting all the bits and then add 1 into LSB bit. In this way we can find out the 2's complement, and whatever the result of 2's complement is added with the number A. So clarify here what is the process to find out 4-bit subtractions. So once again go through this to draw block diagram. First we know that there are 4 numbers, so we take A0, A1, A2 and A3. These are the 4 numbers of 4 bits of number A. Then we need C in, so apply C in here. Next, but what we have to do, we have to take first 1's complement, and 1's complement is nothing but inverting all the bits of number B. So which way we are going to invert all the bits or bits of each and every number? By using NOT gate. So use NOT gate at number B, that is B0, because we are going to invert all the bits. So B0 is also going to be invert, B1 is also going to be invert. In the same way B2 is going to be invert, B3 is going to be invert. So in this way, in the first step we are going to take a 1's complement by inverting all the bits of the number B. Then we have to add 1 into LSB, that is least significant bit, and this is the full adder 1, full adder 2, full adder 3 and full adder 4, and this is called as LSB full adder and this is called as MSB full adder. So we have to add C in, that is 1 into LSB, so C in becomes 1. And what are the outputs? These are the sum, it will be, and this will be input for the next C out of the previous stage. Again this is the sum of second stage, and this will be C out of the second stage. This is the sum of third stage, this will be C out, and this will be sum and C out of the last stage. This is about the full adder subtractor. I hope so you easily identify the comparison between or difference between the both the adders. What we have to do, which rule we are going to be implement to design 4-bit full adder as well as 4-bit subtractors. Okay, then go through with the one more point. If any designer or any applicant want, I need in a single circuit 4-bit adder as well as subtractor, because in these two approach we are separately design adder as well as separately design subtractor, but the circuit which will defines or designs for the full adder as well as subtractor. Let's go with this point to design a 4-bit full adder as well as subtractor. In the designing of 4-bit adder or subtractor, first what we do in adder, we are going to add number A with number B. So we cannot take any invert of number B, as well as we are not add any value in LSB bit, but we are going with the subtractor of A minus B. First we take 2's complement of number B. What is meaning of 2's complement? First take 1's complement. How we take 1's complement? By inverting all bits of number B, and for inverting we use NOT gate. Okay, and for the similar way, we second step we add 1 into LSB bit. This will be concerned with the adder as well as subtractor, but in the same circuit we have to apply adder as well as subtractor. So for that, just remember a exclusive OR gate, that is A and B are the inputs and Y is the output. That is truth table of the exclusive OR. So just read carefully. The number B in the adder, no bits are going to be invert, and in subtractor number B, all bits are going to be invert, as well as we have to add 1 into LSB. For that we have to apply the logic. So 0 0 it will be 0 0 1 1 1 0 1 and 1 1 0. This is the truth table of the exclusive OR gate. What we have to do, we have to divide this truth table into different parts. This is called as part first and this is part second. That is very important, how to design adder as a subtractor in a single circuit. If you observe carefully, just compare output with concern to input B for values of A. If A is equal to 0 for this, what is the output? Output Y. Compare in terms of B is 0 and B is also 0, so Y is equal to B. Okay. In another case, if A is 0, then Y is 1. Y is 1 and B is also 1, so Y is equal to B. This is the first part. Okay. In the second part, for this one conditions of A, if A is equal to 1 and B is equal to 0, Y is equal to 1. Just compare Y in terms of B. If A is value 1, Y is equal to 1 and B is equal to 0. If in second condition A is equal to 1, B is value 1 and Y is value 0. So you observe carefully in these two terms, Y is equal to B complement, because if B value is 0, Y value is 1. If B value is 1, Y value is 0. So we say that Y is equal to B complement. These are the two different parts. This is part first and this is the part second. So by implementing this logic, by putting A is equal to 0, we can implement adder in the same circuit, and by putting A is equal to 1, we can implement subtractor. Okay, and what about the LSB? We'll see what we have to do for the LSB. For first, draw the block diagram of the 4-bit adder as well as subtractor. We need 4 full adders. Okay, this will be acts like this one. This take a XOR gate. Okay, this is the input A and this is the input B, and here is the input for the next term. So this will be input, this is a control input, you can say. Okay, just take, we are not going to do any operation on number A, so number A as it is A0, A1, no change with concern to number A, A3, and this is a A4. Okay, next what we have to do, we have to control on number B. So we have to take first OR gate, exclusive OR gate, with inputs are 2. One is the number B, B0, and another number is a, you can say M, that is a control input, M. This will be continue with this second full adder also. Okay, then go through with the second number, that is number B1. Again this is control bit for exclusive OR gate, so again this will be input for the next OR gate, exclusive OR gate, sorry. This will be B of 2. In this way we are also conclude for the B of 3. So after getting this, just this is a M, we can assume M as an control input. So what is the function of M, how it works, let's explain in this function right now. This is sum 1, this is sum 2, this is output of full adder 3, sum 3, this is sum 4, this is a C out, C into the this stage is C out from this one, again C out of this is C in for this one, again C out of this is C in for this one. This is a full adder first, second, third and fourth. It is called as MSB full adder, and this is called as LSB full adder. And this EM is nothing but control input, and which is given to C in to the first full adder. Okay, first for the adder operation, what we have to do, we no need to change number A as well as number B. So we no need to change any value, so that just consider C in is equal to 0. If C in 0, no need to add any LSB bit with one value, so C in makes 0. Here if we give this bit as a 0, this is control bit. If this is a 0, and what will be output? Output is equal to the B. So we are going to be perform here addition. So again this is going to the second XOR gate. This is again 0. Here output is a B. Here B0. Here B1. Again here output is a B2, and again output is a B3. So there is no change in the output of the exclusive OR. It comes as it is, the number of bits. When we are going to be define a subtraction, at that time we are going to M is equal to the 1. For M is equal to 1, what will be happen? Here 1, when M is equal to 1, this control bit becomes 1, and what will be output? Y is equal to B complement, which will comes in the second part. If control bit M is equal to 1, then Y is the complement of another number B. So this will be gives B0 complement, this again 1, this will be gives you B1 complement, this again 1, it will be gives you B2 complement, and here again 1, it will be gives you B3 complement. So we need for the subtraction first inverting of all bits. So we are getting invert of the all bits of the number B. Then we have to add, second step, we have to add 1 into LSB bit. So this control input is connected to C in, and if the value is 1, then C in becomes 1. In this way we are going to add into LSB also. So this is a circuit which works as an adder as well as subtractor by using a XOR gate to implement some logic to the exclusive OR gate. I hope so you understand the concept of 4-bit parallel adder, 4-bit parallel subtractor, 4-bit parallel adder as well as subtractor. So this is single circuit logic in which we are going to be implement adder as well as subtractor by using some changes or by using a exclusive OR gate. Thank you very much. I hope so you understand the today's video which are covered on the adder, subtractor as well as adder and subtractor. Thank you very much. If any doubt, then please put a comment in comment box.